Hey class, today we're going to start learning about calorimetry. And calorimetry is going to be spanned over a lot of this week, and then we'll have a lab, so we're going to spend a good chunk of time on it. So let's go ahead and get started. For an introduction, the values of delta H, remember H means enthalpy, so let's go ahead and write that. That means, and remember that has to do with heat transfer. It can be determined experimentally by measuring heat flow accompanying a reaction as long as it has constant pressure. Now, the way we do this is we can determine the magnitude, or how big of a heat flow, by measuring how big of a change there is in the temperature. Maybe there's a decrease in temp, maybe there's an increase. And this measurement of heat flow is called calorimetry. And the device we use to measure heat flow is called a calorimeter, which we'll be doing in lab, is building a calorimeter and doing a calorimetry lab. So the more heat an object gains, obviously the hotter it's going to get. It's gaining more energy. Now, all substances change temperature when they're heated, but the magnitude of the temperature change produced by a given quantity of heat is going to vary from substance to substance. So some things heat up faster than other things. So the temperature change experienced by an object when it absorbs a certain amount of heat is determined by its heat capacity, or it's denoted the letter C. So heat capacity here is going to be something important that we're going to get to. Okay. So heat capacity is the amount of heat required to raise the temperature by 1 Kelvin. The greater the heat capacity, the greater the amount of heat needed to increase the temperature. So, for example, water is one of those things that have a very, very high heat capacity. Water takes a bunch of heat from the atmosphere. It takes a ton of heat to even warm up 1 gram of water 1 degree Celsius. And water is a very good holder of heat. You know, if you go to a pool, or say you go to the ocean, it can be 100 degrees out, but the water in the pool is still pretty cool because it doesn't warm up as easily as other things. Okay. So the heat capacity of 1 mole of a substance is known as molar heat capacity. And the heat capacity of 1 gram is called specific heat, and this is what we're going to focus on today. We will have a problem with molar. And specific heat is denoted by the letter C with a little s down here. Now, typically, your units for molar heat capacity and specific heat capacity, they're going to change depending on what you use in the problem. But for the most part, for molar heat capacity, your units is going to be joules per mole times Kelvin. Down here, usually you'll get joules per gram times Kelvin. So those are some common units that you'll use. So specific heat can be determined. Experimentally by measuring a temperature change. Temperature change is denoted by the triangle delta. So remember, whenever you have a temperature change, that is going to be your final minus your initial temperature. So you have to take what you ended with minus what you started with, and that gives you your temperature change. You can have a positive temperature change, or you can have a negative temperature change. And the mass. So mass right here, for our purposes, we're always going to do them in grams. So we measure the temperature change, and we know the mass of a substance, and then we see how much energy is gained or lost in the term of heat. So heat is denoted by the letter Q. Okay. So specific heat, the equation for it equals heat transferred, which is Q, divided by the mass of a substance in grams times the temperature change. I've told you right now that Q is typically going to be in joules. M is going to be in grams. This right here, since it is a change in temperature, it can be degrees Celsius or Kelvin. It doesn't matter since we're finding a difference. Both of these temperature scales go up by 100, from 0 to 100. So it doesn't matter which one we have it in. Okay. And that is why typically for specific heat, we get the unit joules divided by grams times Kelvin, or it could be grams times Celsius. So here's a good example, and this is what we're going to use. It says 209 joules is required to increase the temperature of 50 grams of water by 1 degree Kelvin. So here specific heat is C with a little s. Heat, which is Q, is denoted up here with the 209. It's in the correct units. 50, it's in correct units of grams. And then here's your Kelvin. So 209 divided by 50 is about 4.18 joules divided by grams times Kelvin. And this is actually the specific heat of water. So this is actually a very important number to write down. The specific heat of water is 4.18. So the unit for specific heat that we saw here, joules divided by grams times Kelvin, is dependent on the units that we use in the calculations. So for example, if this was kilograms, then right here, our unit should have been joules divided by kilograms times Kelvin. Or here, if this unit was Celsius, I would have to put joules divided by grams times Celsius. So you have to make sure your units match. Another way that you can rearrange that equation is you can rearrange it by saying Q, which is your heat, equals your specific heat times mass times your change in temp. Whenever you have a positive Q, that means that it has absorbed energy or absorbed heat and your temperature has increased. Whenever you have a negative Q, it means you have somehow released heat and the temperature goes down, it gets colder. So let's try out some example problems and have you guys watch some of these to make sure that you guys know how to do them. The first one, it says how much heat is needed to warm 250 grams of water from 22 degrees Celsius to 98 degrees Celsius. And then remember that number I starred, that's super important. The heat capacity of water is about 4.18. So let's go ahead and set up this problem. My equation is Q equals specific heat times mass times delta T. So we can go ahead and start plugging in things we know. One thing you should do before you start plugging in things you know is making sure that your units are matching. So here my unit is in grams. If you look down here, it has to be in grams. Here, my units in Celsius. Temperature, like I said on the previous slide, it doesn't really matter. Notice these numbers are the same, whether it's in Kelvin or Celsius. So here we have Celsius. So our units are all matching up. And we can go ahead and plug in what we know. We're trying to solve for heat, so we can put X in for that. Heat capacity or specific heat is the CS, and it's telling us right here that the specific heat of water is 4.18. Then we have our mass. Remember, our masses have the same, so gram and gram, we're good to go. And the last thing we have to do is change in temp. So remember, change in temp, delta T, is final minus initial, which means I have to take 98 minus 22. And when you do that, you get 76. Now you can get a positive 76 since our final was 98, but notice that for your temp, you can also put in a negative number. It is perfectly okay to have a negative temperature number there. It just means that the water decreased. Here I can go ahead and solve for X by just multiplying across, and you'll get that X equals 79420, and you have to give it a unit. Well, here we've already used gram, we already used Celsius, so the unit for heat that we have left in our problem is joules, so joules of heat. Now, if I were to ask you to put that answer in kilojoules, the only thing you would have to do to go from joules to kilojoules is divide by 1,000. So another way you could write this instead of just in joules is by saying 79.42 kilojoules. Any one of these numbers is perfectly acceptable as long as you provide a unit. Part B, instead of looking for heat capacity, which uses grams, this one's asking for what is the molar heat capacity of water. This looks way more complicated than it is, but since we already know the heat capacity of water to be 4.18 joules per 1 gram a degree Celsius, all we have to do now is just to cancel out my grams and put moles in there. So the easiest thing to do is just multiply it by the molar mass. So here, if I have grams on the bottom, that means grams has to go on top, and I want to get moles down there. And then all you have to do is molar mass. And again, we're doing this for water. So H2O, we have 2 hydrogen and 1 oxygen, which gives me 18.0148 grams for 1 mole. And if you look at this, you cancel it grams to grams, and that leaves you joules divided by moles times degree Celsius. And notice that if we go back here, joules divided by moles times Kelvin, but remember temperature is interchangeable, so that could be Celsius as well. So here we can go ahead and keep going. And if you just go and plug that into your calculator, you get about a 75.2 joules per mole times Celsius. So there's your answer. So let's go ahead and do a little bit more examples, and I'm going to kind of show you a little bit more. Here it says large beds of rock are used in some solar heated homes to store heat. Assume the specific heat of rock is 0.82 joules per gram Kelvin, and it wants us to calculate the quantity of heat absorbed when we have 50 grams of rock if the temperature increases by 12 degrees Celsius. So again, let's go ahead and put our equation up here. Q equals specific heat times mass times delta T. Okay. And again, we have to plug in what we know. It says calculate heat. So we know that heat is going to be X. One thing to point out is it says heat absorbed. So if it's absorbing heat, that tells me that my answer, it should be positive. So I'm going to say answer should be positive since we are absorbing that heat. If you get a negative answer, that means you have released it. So that just kind of gives you a little hint there. The second thing is the specific heat, and it gives us the specific heat. It tells me that it's 0.82 joules divided by grams times Kelvin. The next thing is you have to look for your mass. So my mass is 50 kilograms. Remember, though, you have to make sure that your units match with your specific heat. Notice that this says kilograms and this is in grams, which means I have to change my kilograms into grams. So 50 kilograms, to change it to grams, I have to multiply by 1,000. So then you get 50,000 grams. So I can plug in 50,000 here. Now your mass always has to be a positive number because you can't have negative mass. So notice that the mass is always going to be positive. And the last thing is your change in temperature. So here, this is where you're going to have to pay attention to those words. It says if the temperature increases by 12. So since it used the word increase, that means I have a positive 12 degrees Celsius. Then you can go ahead and plug this into your calculator, and you get about 492,123. And then you have to come up with a unit for your heat. So if you go back to your specific heat, the unit here I have is joules. So this unit is going to be joules. Okay. And then that brings us to continue practice problems. So it says problem from previous page. We're going to use stuff on the previous page to help us with this problem. So it says, what temperature change would these rocks from the last problem undergo if they emitted 450 kilojoules of heat? I'm going to go ahead and put this back up here. Q equals CS times mass times the temperature change. Here it says my mass is going to stay the same. So if you look at the previous problem, our mass was 50,000. So our mass is going to stay the same at 50,000. It wants to know temperature change, so I'm going to put an X for it. If you go to the last problem, 0.82 was our specific heat. So the last thing that we have to put in is this Q. Well, here, Q is heat. Heat is denoted by Q. It says 450 kilojoules. Well, kilojoules does not match what we had up here for our specific heat unit, which was 0.82 joules per gram Kelvin. It wants joules, kilojoules. So we have to change this. 450 kilojoules. If you're going to change it to joules, you multiply it by 1,000. So 45. 1, 2, 3, 4. Okay. The other thing that you have to pay attention to is your heat. You can gain or lose heat, and that's going to change the sign. So this says it emitted 450 kilojoules of heat. Emitted means that I'm going to get a negative sign. So over here I have to put negative for 450,000 joules. Then you can go ahead and solve. You have negative 450,000 joules equals, if you take 0.82 times 50,000, that gets you 41,000 X. And then you can go ahead and divide 41,000 to get X by itself. So when you take this negative 450,000 divided by 41,000, you're going to notice that X equals about negative 10.975, etc. for your temperature. Now remember, since your temperature is denoted as a change in temp, this isn't what the temperature actually is. This just tells how much it changed. So this negative sign is telling me that the temperature decreased by about 11 degrees, so 10.97 degrees. And you can put degrees Celsius or you can say Kelvin. Either one is acceptable. Just know that it decreased by that amount. So that's the end of today's lesson. For your homework, you're going to be using this Q equals specific heat times mass times delta T, and you're going to be given 3 of those, and you're going to have to solve for the last variable. So let me know if you have any questions, and I hope you have a good day.